Well, a lot of people are like that. So we are doing the quotient rule today. And first of all, we're going to do sort of a proof of the quotient rule, basically derived from the product rule. And so we have a function of x, which is h, and it's made up of a function of x, which is f of x, divided by another function of x, which is g of x. Now, I have deliberately left out all of the x's and all of the brackets just because it makes it a little bit more complicated to write out and perhaps understand if we do this. Now, what we actually do is we just use the product rule when we're developing the quotient rule. And we use the product rule by changing this function of g to g raised to the exponent -1. So this is not the same thing as the inverse function g. Okay? So now this is suddenly g, which is a function of x, inside of another function, which is g to the exponent -1. So we're going to have to use our chain rule when we take the derivative. Okay. The derivative of h, sorry, I'll write my primes just a little bit bigger, maybe, is just going to use the product rule, and we have to use the chain rule. So the derivative of the first function times the second function plus the first function times the derivative of the second function. And notice we have to use our power rule here, and so the -1 is going to come down in front, and we have to subtract 1 from the exponent, so it becomes g to the exponent -2, and then we have to take the derivative of the inside function. So this becomes g primed at x. So, sorry, there's my f primed at x. Okay, right now it's in only a mother could love this form, and so we are just going to reform it a little bit. This is f primed over g. Those should both be g of x. There's a -1 in this term right here, and so I'm just going to subtract here. F, well, that's just f. And g to the exponent -2, that's g squared underneath. And g primed is going to go right there. Okay, there we go. Now, this is a fraction, and we almost have a common denominator, but we don't. We have a g here, and we have a g squared there. And I'm going to use my magical form of common denominator finding, which is least common multiple is g squared. So I'm going to need to multiply top and bottom by g here, and that becomes g squared minus f times g primed, and this is over g squared. And of course, I can always just put those both over the common denominator, which is g squared. Okay, so once again, this comes down to kind of a nice little song. And so it goes like this. Bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So it's kind of a nice little song. It's appropriate for different forms of worship. So what I like to do when I get one of these quotient rule questions is I like to lay out the top function and the bottom function, take the derivative, and then just plug it into the formula. Okay. Let's do an easy one. So here's my function. H is h of x, so it's a function of x, is equal to 2x plus 1 over x minus 2. All right. So my top function is 2x plus 1. The derivative of my top function is 2. My bottom function is x minus 2. The derivative of my bottom function is just 1, which is going to make things easy. So I'm going to box this off so that I don't have to look at it too much. Okay, so the derivative of h at x is equal to the bottom, which is x minus 2, times the derivative of the top, which is 2, minus the top, which is 2x plus 1, times the derivative of the bottom, which is just 1, and this is all over the bottom squared, and so it's over x minus 2 squared. And I can do a little bit of simplifying. 2x minus 4 minus 2x plus 1 all over x minus 2 squared. And so this is 2x minus 2x, which is no x's, minus 4 minus positive 1. And so this becomes minus 5 over x minus 2 squared. And so there's my derivative. Now you will notice that the bottom is always going to be positive, and notice that the top is negative. Basically, the derivative has a negative value. That means the slope to every single tangent to this equation is going to be negative. Okay, so this equation is always decreasing. And if you think about it, it's always got a negative slope. It's one of these rectangular hyperbolas. The slope is always negative. Ooh, I didn't do a really good job of drawing it, but you can see the slope is always negative based on the form. Okay. Now, we have a couple of homework questions from yesterday. And so yesterday we did the chain rule, and some of the questions that you had for the chain rule involved quotients, which you can do with the quotient rule, or you can do them with the product rule using negative exponents. And so when it comes to your test, you can probably just use the quotient rule. So question number 6 from the homework yesterday said, find all horizontal tangents to the function y equals x squared over x plus 3. Okay, horizontal tangents. And so for a horizontal tangent, what is the slope of a horizontal line? Oops. M is equal to, what is that slope? If you said 0 after pausing the video to think, you're right. The slope of a horizontal line is always 0. And so basically, y primed has to be equal to 0. So here we go. We're going to take the derivative, which, by the way, is almost always the thing to do in calculus, is take the derivative. And so my top function is x squared. The derivative of my top function is 2x. My bottom function is x plus 3. The derivative of my bottom function is 1. Okay. So y primed is the bottom function, x plus 3 times the derivative of the top function minus the top function times the derivative of the bottom function, which is just 1. And this is all divided by the bottom squared. Okay, let's do a little bit of expansion and simplification of the top. So 2x plus, oh, that's 2x squared plus 6x minus x squared. And oh, that's all the top. Wow, that was over faster than I thought. This is all over x plus 3 squared. And look, 2x minus x squared. I'm just going to do this. Make them both disappear. That's convenient. Okay. Now, we need to find where this function is 0. That means I don't care so much about the bottom, but I do care about the top. Whenever the numerator is 0, the derivative is going to be 0, the numerator of this expression. So y prime equals 0 when x squared plus 6x equals 0. I go to my old friend for whom to sum is an old enemy, and I factor it. And so this whole thing is going to be equal to 0 when x is equal to 0, or when x is equal to -6. So these are my two locations. Those are my two locations where the tangent will be horizontal. Okay? And so I don't know what this looks like. Some crazy function that's, let's see, it's always positive or something like that. Anyways, it's going to look like that. I've got two places where the tangents are horizontal. One is at x equals -6. Okay, and then I've got another one at x equals 0. Oh, did I ever draw my axis wrong? Anyways, all I really need to do is find out what the y-coordinate of these points is, and I will know what the equation of those lines are. Okay, so I'm just going to take my x's, and I'm going to plug them back into the original equation up there. Here goes all this other stuff disappearing. I just need to find my y-coordinates where my horizontal tangent goes through. So when x is equal to 0, y is equal to 0 squared over 0 plus 3, which is just 0. And so one of my tangents is y equals 0. Okay. My next one is y equals -6 squared over -6 plus 3, which is equal to 36 over -3, which is just -12. Did I get that right? Yes, I think I did. And so the second tangent is y equals -12. Okay, so there are the two equations of the horizontal tangents. All right. Any questions? Did I do anything wrong? All right. This whole horizontal tangent having a slope of 0, we do entire lessons on that a little bit later on.